ET 114, Chapter 17, Series Parallel AC Networks. Just going to go over a couple things with you guys real quick to explain how to handle series parallel networks. So we're going to develop confidence in the analysis of series parallel AC networks, become proficient in the use of calculators and computer methods to support analysis of AC series parallel networks, and understand the importance of proper grounding. We're not going to go over grounding in this video. So when working with series parallel AC networks, considering the following approach: redraw the network using block impedances to combine obvious series and parallel elements, which will reduce the network to one that clearly reveals the fundamental structure of the system. Study the problem, make a brief mental sketch of the overall approach you plan to use. Doing this may result in time and energy saving shortcuts. After the overall approach has been determined, it's usually best to consider each branch involved in your method independently before tying them together in series parallel combinations. When you've arrived at a solution, check to see that it is reasonable by considering the magnitudes of the energy source and the elements in the circuit. And the other thing that they're not saying is know your calculator. You definitely need to have a calculator that can do complex numbers and be very familiar and proficient at using it. I use the TI-89, and there's a lot of examples in the book of how to all the key presses that are involved to figure that out. So the book shows here this circuit, all right, that's showing this example. Now, right away, they just jump right to this here. How did they get there? Like, you might be asking yourself, that's great. What are Z1 and Z2? I don't understand how they jump from here to here. Well, I'm going to fill in the blanks. That's the purpose of this video. So I created some more slides. This is how they got there. So if you go back and visualize this in your head, and let's just give you another example where we have 4 impedances, okay? In this other circuit, we only have 3, but I'm going to give you an example of 4. So first, it needs to be recognized that circuits can be drawn in different ways, where Z represents impedance. All 3 of these circuits are equivalent. So you have a circuit that's drawn like this, it could be drawn like this, and it could be drawn like this. These are just examples of how they can be drawn, and they're drawn differently, but electrically speaking, all 3 of these circuits are exactly the same. So you need to kind of familiarize yourself with that. Then the next step is the difference between series and parallel needs to be understood. Series elements are connected at one end only, and they are in the same path of the current. So in this circuit, Z1 and Z2 are in series. Okay, you can see they're along the same path. There's no breaks in the path or splits in the path going on, and these two by themselves are in series. Parallel elements are connected to each other on both ends. So you can see on Z3 and Z4, they're connected on this end, and they're also connected on this end. Same thing goes for Z3 and Z4 over here, and Z3 and Z4 over here. They're just drawn a little different, but those 2 elements are in parallel. So then you need to simplify the circuit in steps. Since Z1 and Z2 are in series, they can be added together. Likewise, since Z3 and Z4 are in parallel, they can be combined using the parallel operation. Z3 parallel with Z4 it's the same as with resistors. Z3 times Z4 divided by the quantity Z3 plus Z4. Now again, remember, all of these are complex numbers. When we say impedance, it has a magnitude and a direction. So it will, in a rectangular fashion, it'll be R plus JX, or in polar, it will be Z with an angle of theta. But whatever way you do it, your calculator should be able to handle either way, and you don't have to flip between modes unless you're asked to give a number in the other form. Like if you calculate it and your calculator set to polar, you may be asked to give it in rectangular or vice versa. So depending on what you're asked for is the mode in your calculator you need to pick. But it's very, very difficult to do a lot of these calculations by hand with a conventional calculator. Therefore, you do need a calculator that will do complex numbers. So, and that being said, also do not make the mistake of trying to add them all together, like Z1 plus Z2 plus Z3 plus Z4. Okay, that would only hold true if all four of them were in series, which they are not in this circuit. Or try to add Z2 plus Z3 because again, Z2 and Z3 are not in series. All right, they're just not. You have the Z4 involved, and they're not in series. Right now, they're not anything. They're just connected. They are not in series or parallel. I'm talking about just these two elements right here. And likewise, don't do an operation like Z2 in parallel with Z4 because again, in this configuration, Z2 and Z4 are not in parallel. So that would not make sense. None of those conditions exist in this circuit. So let's call ZA Z1 plus Z2. And again, A is arbitrary. I'm just picking a letter off the top of my head. We could call it Z prime. We could have called it Z11, whatever we wanted to call it. The A I'm just picking out of the air. And let's call ZB Z3 in parallel with Z4. So it's just showing you that we're simplifying the circuit down from this thing to this thing. So the final step is you can see that ZA and ZB are now in parallel because they're connected in series. Or I'm sorry, I said that wrong. ZA and ZB are in series, so you can add them together to get the total impedance. So total impedance is ZT equals ZA plus ZB. It's the total impedance because it is the impedance that is in series with the voltage source across the source, and the circuit cannot be simplified any further after that. So the next slide, again, you're looking at ZA and ZB here, and then this is just showing you another way to call it ZT. The arrow for ZT means it's the equivalent impedance looking from the vertical line to the rest of the circuit where the arrow is pointing. So ZT equals ZA plus ZB because these two are in series. So then you find ZT, and again, all these operations need to be done in complex number form on your calculator. You can, once you find ZT, using Ohm's law, you can find the current going through ZT by taking E divided by ZT. And then finally the process can be reversed and in the same steps. Take the baby steps that you use to get to this number. If you try to put together one big long equation at the very beginning, it can get confusing, tough, and it's much more likely for you to make a mistake. So if you take it in small steps, then you can verify your answer. Does that answer make sense? Okay, I'm going to move on to the next step. And then whenever you go backwards, you can find voltages using the voltage divider or Ohm's law, and currents can be found using the current divider. Like example, if you wanted to find the voltage across these two, okay, the voltage from this point to this point, you would have to use the voltage divider, with this being one element and this being the other element, and you know what the total impedance is. So this would be the portion of the impedance of the voltage across here. So it's a ratio. You just use the voltage divider formula. Likewise, if you wanted the current back through, say, Z3, then you know that I is going through these two elements, and then it's being divided between Z3 and Z4. So you would use the current divider to figure out what the current is through Z3. So then the book picks up here, and it simplified that circuit, okay, that we had originally, and it's showing you another example with a current source instead of a voltage source. Z1 is going to be this R element in series with XL. So you add those two impedances together to get Z1, and then Z2 is equal to the impedance of the capacitor. Another example, you have a voltage source here in the middle, and then the current splitting, and it's going this way and it's going that way. And then you have an impedance over here. They called that Z3, which is the inductor's impedance. And then they called Z1, well, they called Z1 the impedance across the impedance of the resistor, and Z2 is the impedance of the capacitor. So from this example, you could add these two together because they're in series, and then the total impedance of these two is in parallel with Z3, which is also in parallel with the voltage source. Another example, they have this resistor, inductor, another resistor, and a capacitor. So they broke it down into these two impedances. So Z1 would be the impedance of R1 added to X sub L, the impedance of the inductor. Again, this is the value of the reactance, and the definition of an inductor is with an angle of positive 90 or J4, and then this would be minus J6, or in polar form 6 angle of negative 90. So Z2 would be R2 added together with its impedance added to the impedance of the capacitor. And then they have another example, determining the voltage across here. It's getting a little bit more complex, but basically what they're doing is they break this down. They're saying this is the first stage right here. So what they did was they simplified it to two impedances here with the current source pointing down. So this current source is pointing down. They have an impedance here, and then they broke it down with another impedance here, which would be the capacitor and the resistor combined. So that's basically it. That's how you simplify these circuits down to an easier form to be able to handle.